So, hi everybody. Great to see you here. This is my first presentation at DPDK Summit ever, and I'm Andrey from NVIDIA Mellanox. And today we will talk about DPDK, about SPDK. Sorry, we will talk about SFT, which is Stateful Flow Table. Okay, I hope everybody able to see my screen. So this is our agenda. We will talk about shortly about what is SFT, maybe short introduction. We will jump to connection tracking for those who are not familiar with connection tracking, and also we will emphasize the SFT connection tracking aspect. Then we will talk about SFT, what is it, mostly basic and high level. Then we'll talk about why we think that SFT should be a part of DPDK. And then Ori will dive into technical details of this library, like interfaces, PMD, changes for RTFlow, etc., etc. And then there will be some example of SFT. So, what is SFT? As I already mentioned, SFT is about implementing a connection tracking library, and connection tracking library inside DPDK. It's about to track the state of TCP streams, UDP, and ICMP connections also. And the other part of SFT, or additional part of SFT, is providing some framework to store context that can be retrieved when you are processing packet. What is this packet? Where this packet comes from in a sense of what connection it relates to. And when we are talking about what connection it relates to, we also can treat it as this is not just a single packet in a state that analyzed in stateless manner, but this is a packet that has history of all previous packets and all decisions that made based on all previous packets, and then we can make a better decision by watching the history of this connection and the content of the packet. So this is something about SFT. This is something that is reminds us the presentation made by Mellanox guy, Shahaf and Ofer on previous DPDK summit. And the talk was about DPDK-based security SDK, as you can see from the slide. And the idea that emphasized here is that if you want to implement one of the products mentioned on the left, like next generation firewalls, intrusion prevention, or intrusion detection systems, web applications firewalls, all those are related to security products. And if you want to implement virtual switch, gateways, or load balancers, etc., etc., you will find yourself implementing some components that will be common, for example, for next generation firewalls and vSwitches and gateways and IPS and IDS. So what are those components? Those components will have some common name, and today I want to show you that this same component is actually a SFT stateful flow table, since all those components need to process packet in stateful manner in the context of all previous packets of the given connection, and they will do it pretty much same, and a library like SFT should help to implement this kind of products. So what is application pipeline that actually same for all those applications that we talked before? First of all, there will be some ingress of packets into the application, and we assume that it will be done by DPDK, since this is all about DPDK, and then once it enqueued into some DPDK queue, it's about to start processing. And first part of the processing will be actually connection tracking, since you need to sign or identify what kind of connections the derived packet relates to. Then there comes an inspection and business logic of the application, which is the application part and application implementation, and I don't think that there will be something that common across all those products we were talking about. And then comes the final part, which is the decision whether to drop or what to do with the derived packet. If everything okay, the packet can be forwarded to its destination. So this is very basic and high-level view of all the application we talked before. Let's dive into some details to make it a little bit clear. So let's talk about connection tracking. So, to talk about connection, connection is something that exchanges messages between initiator and initiatee. Initiator is a source for the first packet. Initiator is actually a responder or the server side of the connection. And when we're talking about flows in SFT, we should take into account that SFT flows are bidirectional flows, unlike, for example, RTE flows, which are actually one direction flows, or it can be or ingress or egress, but not both of it. So we're talking about bidirectional flows in when we're talking about SFT. Let's continue. So how should we identify flow in SFT? In networking, there is a definition that called 5-tuple. For those who are not familiar with this definition, it's source IP, source port, IP protocol, destination IP, destination port. And security, most of the applications like security applications and gateway applications or network processing applications that work on L4 connection context, identifying connections by 5-tuple. It's worth to mention that there is also some types of networking configuration when, if you want to identify two sides of the connection, initiator and initiatee sides. For example, in case of NOT, the 5-tuple, the reverse 5-tuple won't be as a mirror of the initiator 5-tuple because of NOT. So it will change L2 and it will change L3 and L4 header. Let's continue. This is last part of our identifying flows part. So in some networking configuration, it's not enough to have a 5 tuple by the meaning of the inner 5 tuple. Because, for example, for VLAN, when network is actually partitioned, we can't we can have same 5 tuple for different connections that are in different VLAN partitions. And if we have a tunneling configuration in a network like VXLAN, then same inner 5 tuple can be in different VXLANs identified by different VNIs, and in this case we also have same 5 tuple. So there is something that defines 6 tuple when we have a zone and 5 tuple to identify connections when 5 tuple is not enough. Also, connection tracking connection and maintain states. The first state that connection actually signed is new when we see the packet that's not related to any known connection. Then it should pass validation, and if it passes validation, it will be assigned established states. Established state is a state of the connection that already exists, and the right packet also passed all validation. What is validation? In case of TCP, it's TCP window validation and also legal TCP flux transitions. SYN/ACK, ACK handshake, and stuff like this. Those states are also kind of superposition, like connection can be established and tracked. Also, it can be established and related when one connection relates to the other connection. A good example of this is a data connection for FTP. And also invalid state when the arrived packet didn't pass validation state. So worth to mention that this is not all the states that we have for connection tracking, but those are most important to keep in mind, especially when we're talking about some examples. So now we arrived to SFT, which is stateful flow table. And why it's considered stateful? First of all, because it implements connection tracking and maintains connection tracking state. It also can maintain multiple contexts which are opaque for SFT, but meaningful for different application components, and that means that application like firewall, for example, can implement something like different defense components, like, for example, scanning some URLs for regular expressions, and in the other component, it also can do some antivirus checks or states check, and each of those components can maintain its context for the given connection across different packets. So once when packet arrives, it actually is this kind of component can retrieve its context, which maintained across entire connection. Another important part of the stateful of SFT is flow aging, because flow aging is a complicated problem for implementing connection tracking and different stateful applications. So we need to take into account. Flow in the SFT, as I already mentioned, is a bidirectional flow, and the table is something that we should relate to as a data structure that you can view multiple connections, you can link one connection to another connection, or in the definitions of SFT, one flow to another flow. As I already mentioned, FTP example, we can link between data flow to control flow for FTP. And it's also centralized resource management. Let's continue. So now we're back again to look at high level of application pipeline, and as we already discussed SFT, now let's take a look at what is inside SFT actually. So this is also very high level diagram of SFT operations, but now it starts to be internal. So after ingress of the packet, it arrives to SFT, and first thing that it should do, it should make a lookup in the SFT table. And if it's found, this is about established connection. We'll talk about it later, but now I want to focus on what happens if we can't find an entry in SFT table. So it's first and flow packet, or FIF as we call it. What should we do about FIF? When it's first and flow packet, we should do additional validations. Mostly, for example, if we're talking about security application, then it's very good place to check for DDoS. If we're talking about other applications, this is about resource allocation, making routing decisions. For NAT, it's about allocating ports, and for gateways, it's about allocating also other resources. So if validation passed and all needed preparation made and resources allocated, then we are about to create a new SFT entry, and we're about to handle a new flow, and then we pass it to the application for handling. Let's continue. So first and flow packet, we already talked about. This is a missing flow table. I have already mentioned those and allocations, and also allocation of new entry. This is a little bit more boring scenario when actually we handle an existing packet of the existing flow. It's still about validations and updating connection tracking state, both based on previously saved contexts and the content of the arrived packet. That's it, and passing it back to the application for further processing. So what can be further processing? I will mention it here, that, for example, for a security application, it will be making all running it through all the policy defined protection mechanisms like scanning for regular expression in URLs, maybe running antivirus on the content of partially downloaded files for looking up for viruses, and checking different states of more high level protocols to detect some kind of complicated attacks of today. Okay, I have one thing that I have not mentioned that SFT is also about handling out of order packets. Talking about all TCP packets also. So if out of order packets arrive, it can keep it till the in order packet arrives, and then it will be available for draining and processing by the application. If SFT won't do it, then it will be responsibility of the application, and I don't think that every application want to implement its own out of order TCP packet handling. Okay, as already mentioned, SFT also handling aging. We have great aging APIs in RTFlow, but those APIs are single direction, and we want to handle it for bidirectional flows, and we want to assist want the hardware assistance for handling aging. Why it's important to maintain aging of the flows, because if there is a flow that no packets are passing in this flow, it maybe holds some hardware resources and host memory resources, which we could use for new connections, and if we are out of resources, those applications just can't establish new connections, as simple as this. So it's important to maintain aging of the connection and dispose aged connections, and also it's important to prioritize the connections. For example, if there is a shortage in SFT entries, maybe it's also it's application decision, but maybe it's a good idea to keep connections for 1 second instead of, for example, 5 seconds. If there is no packets passing, then this kind of connection should be disposed. Okay, now this is almost the final part of my talk about SFT, is why actually SFT should be part of DPDK, why we need it in DPDK. We need it because we can accelerate it. And the first thing that we can accelerate is actually we can accelerate the lookup in the table, which is really computational consuming tasks, which also requires lots of memory traversal and stuff like this. So we can accelerate SFT lookup in SFT table. The other thing that we can accelerate that I already mentioned, we can do hardware assisted aging of SFT entries or SFT flows. And the most important part of this is that once the connection passes some validations and inspections by software, it can be actually fully offloaded to the hardware when we mark some SFT flows as something that are established and approved by our security or just network gateway for full offload, and then it doesn't actually arrive to the application. There is full offload path to forward the connection to the output to the port. So SFT, why? As I already mentioned, lookup declaration, hard disk extension, full offload, and multiple application needs the same logic. As you can remind, this is a slide that was in the beginning of this presentation. So those are products that can utilize SFT, and I want to believe that I have convinced most of you that for the stuff list in this slide, like out of order handling, identifying connection by six tuple, connection tracking, and application, non-application defined contexts and flow aging. We can utilize the SFT to implement products like firewalls, intrusion prevention detection systems, web application firewalls, and stuff like this. So I think this is a part where I will give the control to Ori. Ori, hope you're ready.
Hi everyone, and thank you, Andrei. I don't have a lot of time. Mostly, I'm going to show you basically the software components and the flow, and try to do an example. And so at the beginning, since everything is in RFC mode, in our stage, so everything is subject to change and everything. This is just sorry. This is just a way to show you how to. Hopefully, this is the concept, but later on we'll see that your help is needed. So basically, the SFT is three main components. The first component is the SFT lib itself. The second one is the RTFlow, which we're already familiar, and the third one is the SFT PMD. Let's dive a bit into them. The SFT API. This is the SFT parameters, and it's mainly includes the following functions. It includes the process mbuf, which actually is the main function. It receives any mbuf received by the applications, and it returns the connection ID and the state of that connection based on the mbuf. So this is the main function that the application will always call in order to check the packet states. The second one is quite similar to the first one, but instead of getting the zone from the packet from the mbuf itself, using the RTFlow, it simply gets the zone from the application. This is the activate flow. Is the first flow that's actually it's the second function the application needs to call, and it's the first call after it sees a new connection starting, a new packet from a new connection. It basically gives the SFT the reverse tuple. So when the next packet that will be received from the other side, the SFT will be able to identify that it already belongs to some connection and return based on that the state. If you're looking at TCP, it also can modify the TCP state. If you're looking at UDP, it can just say that it's the traffic coming from the other side. We have the flow create. This is a function that allows the application to insert flows to the SFT table without prior seeing the mbuf. If until now we saw the application saw the mbuf, analyzed using the mbuf process, and then it added the rule automatically by the SFT. In this case, the application itself says, I want to add this flow. For example, for such scenario, maybe FTP connection that after the connection itself to transfer the data is in a shadow connection, and we already want the first packet of the shadow flow to be in a ready state to save the offloading, to save the handling of the application. The last main function is the set context, which allows the application gives the application the ability to change the state. And we'll see that in a moment. Basically, after the application runs install logic, it can change the state accordingly, and this will affect the hardware. Like we said, our main SFT function that we want to support is to achieve offloading. And in order to do that, the state must be changed inside the hardware. Okay, now we'll see the RTFlow component. The RTFlow component is the basic component that we already have in DPDK and is responsible for all ETH traffic that's arriving or sent. So basically, we are planning to add a new action that says SFT, which will mean actually send this packet to the SFT and go somewhere. For example, as you can see in the following rule, sorry, one slide back, 1 second. As we can see, we have a flow create. We have a flow create, and we're creating a float that catches all traffic, all ETH traffic, and we're sending it to SFT. After it passes through the SFT, it will be marked with some value, with some state actually, and then we'll jump to group 2. It's the application responsibility or function to say what it wants to do with such a traffic. We'll see that later in the example itself. In addition, we are adding a new item that will allow to do the matching. For example, in this case, in group 2, the application will answer the flow that if the state is invalid, for example, go to index 1, queue index 1, while if the state is established, for example, do jump to different report or jump to hairpin queue. We'll see that later in the example. Okay, the SFT PMD. Like we said, the main purpose is the offload, and each hardware is different than the other one. So basically, the SFT PMD is part of the ETH device because it belongs technically to the same port, but it's not accessible anywhere beside from the SFT. And it allows to insert the flows, the offload rules that are inside the hardware, and to basically read the state of the packet on the restore state. We'll see that in a minute, but basically think about it that if the application has a miss, it needs to know the state, and the state it's stored somehow on the MBUF using some kind of property or using the mark or metadata. So this PMD knows how it saved the data and how it should restore the data. So basically, it has the most basic API we can think of. It has the entry, which creates a new rule in the table. It has the destroy, and it has the decode function that is actually, it gets the MBUF and based on internal logic, extract from that MBUF the connection ID and the connection state in order to pass it to the SFT lib. Again, since it's different hardwares, each hardware may decode those states in the hardware differently. So that's why it's inside the PMD, the decoding part, and not in the SFT itself. Okay, let's look at a small security example. We look at a simple gateway application. It gets UDP traffic on a given port. And forward it after some security check. Basically, think about it. It collects packets until it runs some regex and it matches that. For example, it's for a known application, and so it's allowed to pass. Then it forwards all the packet to the selected port using hairpin. In our case, this is in the end will be the full offload. As we can see, from our logic, we have first of all, in the green, it's the hardware. So the packet arrives to the hardware, it does five tuple match and checks the state. The reason we also do 5 tuple match is because maybe we want to encap the packet differently on the output, or we want to do some kind of a NAT. So we have a 5 tuple match and we check the state. If the state is equals to established, then basically the applications automatically send it to hairpin queue, where it automatically will be routed back to the wire. Of course, there is before sending it, it can be do encap or any other actions that are supported by RTFlow. In case the 5 tuple doesn't match or the state is not established, then we have the blue part, which is the application. It adds the packet to the security client. It checks security. For example, it wants to see that the target, for example, is Netflix or any other application in this case. Then it changes the SFT state to established after we have some packets. It gets to the state where it can change the established. Then the application sends all queued packet to the wire, while all new packets will arrive automatically to the hairpin and do the requested actions. Okay.
Ori, do we have more slides? It would be time for some question, if possible.
I'll just show this slide. We have more slides, but again, I'm running out of time, so I just will show you this, and I will show you the last slide, which is the most important one. So basically, as we saw here, we have the ingress packet arrives. It's detected by software by SFT hardware. It's marked either with some kind of state. If the state is established, it's continue processing. Otherwise, it's just runs to the app logic. The app logic query the SFT for the state. The SFT calls the SFT PMD for the state. And then it modifies later until the app logic changes it to established. Again, since we're running out of time, and the most important thing I want to do is the last slide is this one. 1 second. This is actually a call for action and for help. We submitted this RFC about a week or two ago. We are working very hard to get to the 2011 milestone. It's a very hard deadline, and we try to match it. But in order for us to do that, we need reviewers, and both me and Andrey are NVIDIA employees, and we try to think of the best way for all companies involved, but of course, we cannot think of everything. So anyone who wishes to review is more than welcome. Anyone that can have any ideas or something that we're missing, something he likes better, something where we're doing good. Always positive feedback is always a good one. We'll be more than happy to hear. You can find here where the patches are for the RFC. You can find my contact and Andrey contact. So again, any review help or any other help is greatly appreciated. Thank you. Questions?
Yeah, questions. And
Andrey, please explain the question about the races.
Oh, okay. So about the races, if we're talking about processing of the packet of the some flow, so one flow can simultaneously be processed only by single context, which means if by some reason there is 2 CPU cores that trying to acquire flow for processing, only one CPU will receive the flow and the other will be blocked till then. There is no simultaneous processing of flow, and but there is a way to prevent the situation when you have a race on flow by configuring the application the way that packets from both directions arriving to queues that are processed by the same CPU. So for given flow also. So this is something that from one side it's a application developer responsibility, but from the other side this is something that can be implemented, and those races won't break the application and can be handled nicely. But even if those races are can work. Okay, so maybe one more question, or we are out of time. It's 5 o'clock. Yeah, Thomas, Ori.
Maciej is asking one more question about the delay. If you can read it in the chat. How about a delay between processing packets and establishing flows in hardware?
Ori, do you want to answer this one?
Yes, technically the delay can be minimal, but in any case, even if there is a delay, for example, or if the packet already received and the state was changed, technically the packet may be already in the queue, in the RX queue, while you're changing the state. So technically there always possibility that you change the state. So the application will receive that the state was established, and then it needs simply to send it itself to the wire again, because there are always some possibility that there will be packets after the established that application will get, even if it's in the same second we insert the flow, the packets may be already inside the software, inside the queue. So the application will handle such minimal misses. Is that answer the question? No, the application should not track the state. No, the application is not tracking the state, simple because when it gets a packet, it always asks the SFT. The SFT will tell him what the state is. So basically, after the application changed the state to any state, next packet arriving to that state, even if it's established already, will get the established. It will get the last modified state. So is that answer the question? So only one entity is controlling it.
So understanding from Maciej that it's a synchronous lookup.
Yes and no, it's support. But again, the assumption is just like, since we are working with DPDK, all packets from specific connection will arrive by almost 100% to the same core. So from two different cores, you can access, and there will be no consistency because you will probably never get a connection, the same connection on two different cores. Because if you're doing RSS on the connection, for example, on the input packet, it will always go to the same queue. So basically, you can support multiple connections simultaneously, but each connection is thread safe. Yes, multiple English L core software. Yes, but each L core assumes to handle the same connection all the time, basically. So we can say that we have 3 cores, and on each core we have different connection, and everything runs simultaneously, and you don't need to do any locks. If, for example, it's possible, but it's impossible and it's not supported to say, for example, the same connection can arrive on 2 different threads. Is that answer the question?
I guess yes, sorry, it's answering.
Okay. Again, thank you very much for joining, and sorry that we didn't show the example, but.
Okay, if any more question, you can stay here in the chat, etc. Of course, yeah. But really, I encourage everybody to engage in the mailing list.
Okay, so thank you everybody, and you feel free to write to me and to Ori to contact us for questions. And once again, thanks a lot for joining the session.
Again, Morten, if I spell your name correctly, again, feel free. You're more than welcome to even call me using Skype or anything, and I'll be more than happy to talk to you. Okay. Thank you. Bye-bye.